হ্যালো,
আসসালামু আলাইকুম।
আমার কথা শোনা যাচ্ছে কি?
Yes, sir. Yes,
Okay.
sir.
So last night, my mother was infected by coronavirus, and she was admitted to the hospital. We feared that my father also been affected, and also we are fearing that myself and my wife also infected by the disease. So pray for us. Let's see what happened. Okay, let's start with our class. I am sharing the lecture. Okay, we are continuing our pursuit to design of gating system. Last class we introduced the gating system. What is it? How it works? What are the common features of the gating system? What are the components of the gating system? In this class, we will end our introduction about the gating system. Here, we'll talk about identifying different type of gating system, and we'll analyze the factor controlling the function of the gating systems. So when you design a gating system, what are the aspects that we keep in mind during the design? And one special topic that is for narrow channels. If the casting section thickness is very thin, then one important element is we know surface tension that comes into effect, and it controls the flow of the liquid metal. So how we deal with this narrow section casting during design of a gating system, that is our last aspect of today's class. So let's talk about type of gating system. In general, there are two different types of gating system. One is called top pouring and one is called bottom pouring. We are keeping in mind that it is solely based on how the liquid metal is introduced into the mold cavity. Previously, we are classified different of a pouring system. One is called a vertical pour, one is horizontal pour, etc. In this case, we are talking about how the liquid metal is entered into the mold cavity. So top pouring means liquid metal is poured directly into the mold cavity, and the bottom pouring means we are entering the liquid metal through the gating system from the bottom of the casting. So from the bottom of the mold cavity. For the time being, just ignore this part. This is the feeder. We are saying that we'll design it later on. So here, liquid metal is poured through the feeder onto the mold cavity. And here, we are pouring the liquid metal from the bottom of the casting. This is called bottom pouring system or bottom gating system. And this is called top pouring system or top gating system. And between these two systems, there is another one which is called side pouring system. That means liquid metal is entered into the mold cavity through the partition between the cope and drag. So there is also some degree of fall from the parting line. So we'll see a certain damage in this liquid metal during this system. So let's talk about these two in a little bit detail. So it is a top pouring system. So liquid metal is pouring under the action of gravity, and we have said that what does mean the under the action of gravity? As liquid metal poured by gravity, so velocity is always increased, and at the same time it is poured directly onto the bottom surface. So there will be a lot of slashing and lot of turbulence and lot of fragmentation of the liquid stream. As a result, if the liquid is aluminum, for example, that means those alloys which are readily oxidizing in nature, so they tend to damage much in this type of system. On the other hand, here we are pouring the liquid metal from the bottom, so it is against the gravity. Since it is against the gravity, So velocity, we are hoping that velocity will decrease, turbulence will minimize, and this will aid aluminum types alloys to have a good casting. So these are the two common aspects of bottom pouring. So it is velocity increases, turbulence is much, here velocity decreasing, turbulence is less. There are other common features. If we see this table, so liquid pour through the top gate and the liquid here from the lowest part of the gating system. Simplicity for molding, we have seen that. Don't bother about the design of the gating system. Uh, and yield is high, obviously. On the other hand, if you have to design a bottom pouring system, there is a lots of complexity. We'll see later. So design of bottom pouring system is a bit critical, and yield percentage is low. Pouring is rated by gravity, as you're saying that faster pouring rate and lots of less liquid fluidity requirement. We should mention this point because if you see the textbooks that we are following, for example, Heinz book, Bailey's books, all those books written in the 70s or 50s even, 60s even. And in that case, period of time, the only two metals commonly used are steels and cast irons. And these type of alloys are has low fluidity. So one purpose of casting was that how quickly we can fill the mold cavity. So fluidity is an issue because steel is very rapidly solidified. So as a result, top pouring is always preferred, and all the gating system that are used in those textbooks, you will see the top pouring system. On the other hand, in the bottom pouring system, filling against the gravity, so pouring is slow, and more fluid is fluid liquid is preferred because velocity is decreasing, so time is more needed to fill the mold cavity. So you need higher fluidity of the liquid metal. Severe splashing and turbulence and mold erosion because of the high velocity of the liquid metal. On the other hand, eliminating splashing, turbulence, mold erosion because of very slow pouring rate and very reduced velocity of the liquid metal. Oxidation of liquid metal resulted because of this splashing and turbulence. Quiet entity of the mold cavity, less turbulence, less oxide formations. Favorable temperature gradient. This is another good aspects of the top pouring system. What do you mean by favorable temperature gradient? When you pour the liquid metal from the top, so just imagine the liquid metal pouring is, you are pouring for about 1 minute. Casting is relatively huge. So the first liquid you used will be a little bit colder compared to the last liquid that you're pouring. So last liquid will be relatively hotter and the first liquid will be relatively colder. And as the liquid is colder, so your specific gravity or density will be a little bit higher. Those liquid metal you pour last, because of the high temperature, the density is a little bit lighter. As a result, last liquid will stay always on top. The first liquid will always stay in the bottom. So the first liquid temperature is reduced. So solidification will start from there and it will go upwards because topmost liquid is hotter. So, and this is the favorable temperature gradient. That means pouring solidification is occurring from the bottom towards the liquid metal entry. On the other hand, if we pour from the bottom, so first liquid is going up, last liquid at the bottom. So last liquid is hotter, but their density is less. The first liquid is colder, density high. So again, we are saying that the temperature gradient is not supposed to be this way. Temperature, hotter liquid should be on the top, colder liquid should be on the bottom. So there is a motion of the liquid, which is called convection. And because of the motion of the liquid, certain things can happen. Effects can generate it, effects can mix up, oxide can flow, move, etc., etc. So unfavorable temperature gradient in terms of solidification, in terms of oxide or other defects movement. Particularly unsuitable for oxidation-prone alloys, for example, aluminum alloy, magnesium alloy. So if you cast using top coating system for this type of alloy, turbulence will damage your casting or can damage your casting. On the other hand, bottom pouring, we prefer this one. We will advocate this type of pouring system in our design purpose. This is a general purpose filling system we will use, and they are particularly suitable for oxidation prone alloys. So aluminum, magnesium, they are excellent for bottom pouring system, and particularly suitable also for heavy casting. Since heavy casting, so it requires more time to start solidification, and during this time, this unfavorable temperature gradient can be minimized. So because of the convection, colder liquid can go down and hotter liquid can go up, and solidification doesn't start yet. So for heavy casting, this system can be suitable or is good for producing better casting, better quality casting. So schematically, we can have this type of gating system. First one, from the top, we are saying this is the top pouring system, gravity cast top gated system. So here is the liquid metal entry, and we are saying that this is very poor. On the other hand, slight modification, top pouring, but with liquid metal entry from the side. Similar kind of scenario. And this is the side gating system. Again, there is a significant amount of fall of liquid metal from the gate, and usually poor. This is the bottom pouring system, not to our likings, but sometimes suitable, sometimes acceptable. And this is the ideal condition for a bottom coating system. Liquid metal is entered in the mold cavity from the bottom. So this is the vertical bottom gated system, which is excellent for producing good quality castings. This is a special case. This is the counter cavity filling system. We said it in our first class. We'll talk about this a little bit later. This is the, by the way, this is the excellent pouring system. We'll tell why later. So if we see the whole running system with the casting, so this is a top gated system, and you will see this type of picture in the textbooks. So we have a conical cup, so liquid metal pour here, and this is a sprue. Forget about reverse taper things, we'll talk about later. This is a sprue, and this is the sprue base, and this is the runner, and this is the gate. There are two gates, and this is the casting, and on the side of it, there is a feeder. So if we see the motion of the liquid, so liquid metal is pouring, is going down, horizontally, going down, then going down. So all the time it is liquid metal is going down. So velocity thereby increased all the time. So turbulence will be maximized. And why we selected this type of things? Because we want to fill the mold cavity as quickly as possible for steel casting and other ferrous type of castings. And we are saying that this is the worst type of casting because of the quality of the casting we will tend to generate. And this is the side gated system. Again, liquid metal pour from the side or parting line. And this is the satisfactory bottom pouring system. So instead of conical cup, pouring cup, we use a pouring basin. This is called pouring basin. Then instead of a round sprue, we used a rectangular sprue. There is no well or bottom of the screw, horizontal channel which is runner. On top of it is a gate, and gate in liquid metal enters through the gate at the bottom of the mold cavity, and liquid metal goes up. So the only this part, in this part liquid falls, and from here this is the lowest point of the mold cavity running system, and from here liquid metal always going up. So from the runner it goes up to the gate, and then it goes up through the mold cavity. So liquid metal is going up against the gravity, velocity will be decreasing, turbulence will be minimized. So we are saying that this is a reasonably satisfactory gating system. Top fed gating. Top fed means liquid metal going up. Okay, this is a version of the bottom pouring systems where the channels are even more narrower. So it becomes, instead of this one, here is a very narrow screw. It could be rectangular, it could be circular as well. And the runner is very slim, very thin, and gates are also a small section. As a result, the liquid metal requirement in the gating system is very less. So percent yield is increased, and ultimately we'll see that because of the constriction or because of the narrowness of the channel, liquid metal will have a very small opportunity to have turbulence, to have splashing, because simply they don't have any enough space to accommodate for those splashing and turbulence. So we'll see that this is one of the most effective gating system, and we'll try to design these type of systems later on. So again, we are advocating the bottom gating systems. Although system is necessary, but it is not a sufficient criteria, because bottom system, design of bottom system is very difficult. So it is very easy to design a bad bottom gating systems, and a bad bottom gating system is always worse than the top gating system. We see some example. This is a bottom gating system, but it designed badly. Because of that, there is a lot of turbulence, a lot of splashing. The velocity of entry is very high. So although we are using bottom pouring system or bottom gating system, this is bad. Similarly, this one. This is a bottom pouring system, but liquid metal enters to the mold cavity directly. As a result, the velocity of the liquid metal after this high fall cannot be controlled. Liquid metal flows with this very high velocity into the mold cavity. So it will strike the opposite end of the mold cavity, and it will damage the other side, and there will be a lot of splashing, mold erosion, and so on. So although it is a bottom gating system, but because of its design, it is very bad. So it is much better. The velocity is contained, liquid metal going up in another narrow channel. So the velocity is hoped to decrease. So this is a much improved version of bottom system compared to this one. Even then, this is not good. We can do much better using this. Why this is good compared to this one? Because liquid metal is moving up to this much. Liquid metal here moving from here to here. So distance of movement of liquid metal is minimized here. So this is a better than this one, but certainly this is the much better from compared to all these four gating system. So here,
Sir,
this.
sir, I haven't understood the last three gating systems and how their quality increases. Can you please explain it again for us?
Which one? Which one? These three or previous one?
No. This one is these are correct, but but except for the top left, the remaining three pictures are not understandable for me. Why they're becoming better and better as we progress?
These
Can
three?
you please? Yes, these three.
Okay. লিকুইড মেটাল এখান থেকে যতটুকু মুভ করছে সেই মুভমেন্ট অফ দ্য লিকুইড মেটাল ইজ ভেরি হাই এবং যেহেতু লিকুইড মেটাল এখান থেকে একটা ন্যারো চ্যানেল দিয়ে উপর উঠতেছে সো একটা বড় জায়গা আছে স্প্ল্যাশিং করার জন্য মুভমেন্ট করার জন্য লিকুইড মেটাল ইফ ইউ কম্পেয়ার দিস ওয়ান উইথ দ্যাট ওয়ান এখানে লিকুইড মেটাল মুভ করছে আপ টু দিস মাচ সো এখানে জায়গা কম ফর লিকুইড মেটাল মুভমেন্ট and liquid metal যদি নড়াচড়া করতে না পারে splashing will be minimized. So that's why, although it is a bottom getting system, this is also a bottom getting system, but movement is minimized here compared to this one. So turbulence will be less in this case compared to that one. বোঝা গেছে কি?
Yes, sir. Somewhat understood.
Someone. Okay, we'll see later with again there. There is another special case we are saying that this is counter gravity filling system. In this case, there is no vertical fall of the liquid metal. There is a one chamber. Inside the chamber, this is our crucible. So we put our metal alloys, melt it here. Inside, it could be a vacuum chamber. So liquid metal enters into the mold cavity by the action of gas pressure. So we applied gas pressure, and because of the pressure, liquid metal rises through this tube and into the mold cavity. So by controlling the gas pressure, we can control the upward movement of the liquid. So we can control the velocity of the liquid metal entry into the mold cavity. And all the time, liquid metal is moving as we allow it to move. So velocity is solely under our control, and depending on the alloy, we can increase or decrease the velocity of the liquid metal. So all the time, it is moving against the gravity at a very low speed. As a result, there are absolutely no turbulence, nothing. So this is a very good failing system with no turbulence, and the casting quality is of supreme quality. Similar to this, there is another system. This is also a counter-gravity system, and this is called Cosworth process, invented by Professor Campbell. Here, furnace is open into the air. From the melting furnace, you pour the liquid metal into a chamber, which is called folding furnace, and there is an electromagnetic pump. And by using this pump, you can flow the liquid metal through this channel or through this tube to the casting. Again, similar thing, liquid metal is moving upwards under the action of the electromagnetic pump. So velocity is controlled. Liquid metal is moving in a controlled way into the mold cavity. So again, there is no turbulence. So casting will be of supreme quality. So this is called counter gravity filling system. Obviously, this is an expensive process. So if you need very good quality casting with the defects minimized or even eliminated, you can use this type of casting. Obviously, these castings are not suitable for general purpose castings because of its expense. Okay, so we're saying that the purpose of the gating system is to have a screw and fill the liquid metal through the screw in such a way that the screw will be filled very quickly. There will be no air, so that there will be no turbulence or gas entrapment. The screw will be filled very quickly, so that there will be no air entry, and then there we have a runner and gate. The liquid will be contained through this runner and gate. Contained means there will be no chance of movement of the liquid metal through this narrow channel, so that no splashing will be allowed. So we have a screw. Its purpose to fill the liquid metal very quickly, so that there is no air inside the liquid. And when the liquid metal enters into the horizontal channel, which is runner, liquid metal cannot move because of the narrowness of the runner and the narrowness of the gate. There will be no splashing, no turbulence, no vena contracta. Vena contracta. There will be no vena contracta, so there will be no negative pressure zone, so that air can enter into the mold cavity. So that is the main aim of designing the gating system. As we prefer bottom gated system, so base of the sprue should be the lowest point of the whole gating systems. And once the sprue bottom is attained by the liquid metal, then there is only chance of liquid metal go up. So always liquid metal is going upwards. As a result, velocity is decreasing continuously. And liquid metal is moving in a controlled and progressive way. So far as possible, the liquid should be slowed as it goes. So if possible, we will allow the liquid metal to slow down, so that velocity can be decreased and liquid metal enter the mold cavity in a quite calm manner. So our target is to enter into the mold cavity. The velocity of the liquid should be between 0.5 and 1. So we say that this is the critical velocity. So if we can maintain this velocity while the liquid metal enters into the mold cavity, we are okay. So in this way, a good, reproducible casting will be generated. Okay, so the top coning system and bottom system we concluded. Then there is another type of system which is called pressurized gating system and unpressurized gating system. So what is pressurized gating system? During this system, from the bottom of the screw, liquid metal is moving and the channel of the liquid movement is constricted gradually. So you are reducing the area of the channel, and because of that, the velocity of the liquid metal is continuously increased. And at the same time, liquid metal is experiencing a certain back pressure. For example, আমরা যখন রাস্তায় যাই, 3 লেনের একটা রাস্তা সামনে যেয়ে নিয়ে হয়তো 2 লেন হয়ে গেছে, এবং আমরা অবভিয়াসলি যখন ওই মাথায় যাই সবসময় একটা ট্রাফিক জ্যাম পাই, বিকজ 3 লাইনটা 2 লাইন হয়ে গেছে, ওই জায়গায় যেয়ে নিয়ে গঞ্জাম লাগে। সিমিলারলি হিয়ার, লিকুইড মেটাল একটা ওয়াইড চ্যানেল থেকে আস্তে আস্তে ন্যারো চ্যানেলে যাচ্ছে, অ্যান্ড ন্যারো চ্যানেলে যাওয়ার সময় সে অলওয়েজ একটা ব্যাক প্রেশার ফিল করে, অ্যান্ড বিকজ অফ দ্যাট ব্যাক প্রেশার, liquid metal have a chance to fill the channel completely. So that's the advantage. As the area is reduced, because of the back pressure of the liquid metal moves this way and it fills the mold running system. So in pressurized system, area of the channel is decreasing at the front continuously. Velocity of the liquid metal is increased continuously, and because of the back pressure, there is a greater chance to fill the running system completely. So if we use the sprue base as a reference point, for example, 1 square inch area, then runner area is reduced, it is 0.75, and gate area again reduced, it is total gate area is 0.5. So 1 is to 0.75 is to 1 হচ্ছে 0.1, individually যদি বলি 0.5. So at the continuously area is decreasing. So this is the pressurized system. In the unpressurized system, exactly the opposite. The bottom gate area, bottom screw area is the smallest area, and from that or there on, the area is expanding. And as the area is expanding, the velocity is decreasing. So as the velocity is decreasing, the chance of turbulence is minimized. This is the sole purpose of this system, minimizing turbulence. Although there are a lot of disadvantages of this system, but the purpose is to minimize turbulence. So if we see that it is 0.5 inch square, here it is 1.5 inch square, the total is 1.5. So 0.5 is to 1.5 is to 1.5, although it can be 3 as well, or even more. So we can increase further. So the idea is the area is expanding, velocity is decreasing. But if we increase the area, there is no back pressure of the liquid. As a result, the chance of entering air into the mold cavity because of not failing the, not mold cavity, sorry, running system, because of not failing the running system completely by the liquid metal is a problem. So there will always chance for incomplete failing of the running system in this type of getting system. So again, if we compare a little bit, in the pressurized system, gate is used as a choke. Okay, so this is the choke. What is a choke? Choke is the smallest area of the running system, and this is the point where the velocity of the liquid metal is calculated. So this is the reference point. So smallest area of the canning system is known as the choke. So if we say that our target is the liquid metal entry velocity will be 1 meter per second. So we'll calculate 1 meter per second in this point because this is the smallest area and it will have the highest velocity. On the other hand, in the unpressurized system, screw area is the choke. Since this is the smallest area, so velocity will be the highest. So our target 1 meter per second. Here will be the 1 meter per second, and after that it will always decrease. Okay, so screw base is the choke. Velocity increases as the liquid flows from screw to runner, and here velocity decreases. Turbulence resulted, turbulence minimized. So that we said that this is our main target. Getting system is kept full due to the back pressure. This is one advantage of pressurized system. Here, you need special precaution to make it kept it full. Velocity in each multi-board gate is equal. So here we have used 2 gates and velocity in these 2 gates are equal. But here it is different. It will be different. And to maintain same velocity in these 2 gates, or if we use 3 or 4 gates, maintaining equal velocity in all gates is a challenge, and you need special measures to do that. Volume of the getting system is smaller because we are decreasing the channel. So volume is smaller, so casting area is very high. On the other hand, here we are expanding the getting system, so it has a chunky size, and yield casting will be always lower. But because of the turbulence, we use this type of system in our design. Now, we are saying a lot of bad thing about pressurized system. What are the bad things? Because turbulence is the main point. Nowadays, later on we see that most of the defects, origin of most of the defects is turbulence. So we are very cautious about how to minimize the turbulence. And because of that, we are saying that pressurized system is bad because turbulence is increased because of high velocity. But this pressurized system have been used for so long for casting gray iron or casting steel. Again, we are saying that in our textbooks, these type of systems are used. So why we use it now? What are the problem of using this type of system nowadays? Okay, first of all, this is because of this green sand system. In your lab classes, use green sand system. That means sand clay system. Bonding is done by the clay and water. So When you use cast iron has a special relation with green sand. What is the relation? Oxidizing environment in green sand mold produce liquid silicate film on the surface of the liquid iron, and this silicate film protect the liquid metal. And since it is liquid, so there is no solid oxide film commonly found in aluminum or other alloys. And because of that, turbulence is not a problem for this type of system. Gray iron, green sand system, turbulence is not much of a problem. And we tend to get good quality casting, even the velocity is very high. But problem is, nowadays, we no longer use green sand system. To have quality casting, we use chemical binder, and we use lots of mold additives. And these type of additives and these type of chemical binders are not suitable or are not doing much help that we usually found in this type of system. So sensitivity of turbulence is minimized in this case. As a result, turbulence will give you bad quality castings in these type of molds. Another thing, use of oxidizing alloying elements such as magnesium or chromium. So these are oxidizing, so turbulence is bigger concern in this type of alloys. Lastly, rise of level of standards required of castings. Nowadays, we have very restricted standards. Previously, for example, if 1 millimeter size of defects is allowed, nowadays we cannot. Size of the defects, tolerated size of the defects is reduced further. So nowadays, for example, we cannot tolerate more than 0.5 millimeter. So because of the restriction in standards, we no longer accept such degree of turbulence in our casting. As a result, pressurized system is bad nowadays. This is a X-ray radiograph example. That means we are doing castings, and we are getting the video using X-ray radiography. This is a side pouring system, and this is a bottom pouring system. We see a lot of turbulence splashing in the side pouring system, and we are also finding a lot of turbulence in the bottom pouring system as well. Why there is a lot of splashing? And this is so liquid metal hit the far end and then roll back, and because of the wide channel of the running system, this type of backfilling is allowed, and because of the backfilling, turbulence is generated, air will be mixed up with the liquid metal, and we'll have a bad castings. So although it is a bottom pouring system, an unpressurized system will get bad result because of the design of the runner in this case. There is another example. So this is the sprue. It's a thin sprue base, and it is a runner. Liquid metal is flowing, hit the far end wall, roll back, and then going up into the mold cavity. There is a fountaining effect, not much, and then it's rolled back again and starts filling the mold cavity. Not much fountain now. It is progressing in more or less calm manner, but because of the early damage, because of this early splashing and fountaining effect, we tend to get lots of crack in the liquid metal. You're saying that this is the white area, these are the cracks. So ultimately, we generate a lots of crack in the casting. So design, even the bottom pouring system or unpressurized system, designing of the system is very critical. It will give you better quality casting, but designing is very crucial. There is another one process, naturally pressurized system. So we have pressurized system we have unpressurized system, and then we have naturally pressurized system. Probably from next year, I tend to advocate naturally pressurized system, but for this year, up to this year, we have used unpressurized system. So what is a naturally pressurized system? In pressurized system, the area is reducing at the ahead of the running system. As a result, velocity increasing. In the unpressurized system, the area is increasing, so velocity is decreasing ahead of the running system. In the naturally pressurized system, we tend to follow the flow of the liquid metal. So the area of the flow of the liquid metal, we design the gating system in such a way that it will always follow the flow of the liquid metal. So if the flow of the liquid metal is like this one, so the area of the channel would be like this one. So there will be no movement of the liquid metal, and we tend to contract a little bit. So if the flow of the liquid metal is, let's say, 5 millimeter square, we reduced it 4.5, so that there will be general pressure. So there will be no localized choke. So in the just like pressurized system, there will be no choke at the gate. For unpressurized system, there will be no choke at the screw base. There is no choke at all. The whole running system will act as a choke because it is pressurizing all the way to the liquid metal. So liquid metal is always at the permanent contact of the walls, and the gently is pressurized by the liquid metal. So effectively, the whole length of the running system acts as a choke. So it is kind of a continuous choke principle and an uniformly pressurized system. So the concept is to design the flow channel so as to follow the natural form that the flowing metal wishes to take, and at the same time develop a natural back pressure throughout the system. So basically আমরা যেটা বলছি যে চ্যানেলটা এত ন্যারো হবে যে আমরা লিকুইড মেটাল চ্যানেল দিয়ে গেলে পরে লিকুইড মেটালের ফ্লোটা যতটুকু হবে চ্যানেলটা ঠিক ততটুকু ডিজাইন করা হবে, বরং তার চেয়ে একটু ছোট করা হবে যাতে করে লিকুইড মেটাল অলওয়েজ রিমেইন ইন কন্ট্যাক্ট উইথ দ্য ওয়াল অফ দ্য মোল ক্যাভিটি রানিং সিস্টেম ক্যাভিটিস, এবং একটা প্রেশার এক্সপিরিয়েন্স করবে অ্যাজ ইট ইজ মুভ through the gating system. Thus, despite the melt having a velocity well above the critical velocity, because it is decreasing and it is a long high fall height, just like pressurized system, so velocity is very high. Jehetu it is not unpressurized system, so area বাড়ছে না, so velocity decrease করছে না. So initially the velocity that সে পেলো during the fall, সেই velocity নিয়েই লিকুইড মেটালটা মুভ করছে, কিন্তু যেহেতু আমি চ্যানেলগুলোকে চিকন করে দিয়েছি, অ্যাজ এ রেজাল্ট হাই ভেলোসিটিতে যে টার্বুলেন্স হবে, ওই চ্যানেলটা এত ন্যারো, ওই টার্বুলেন্সটা লিকুইড মেটাল করতে পারছে না, এখানে কোনো রকমের স্প্ল্যাশিং হতে পারছে না, বিকজ আমি একদম সরু করে দিয়েছি, এর ভিতর দিয়ে লিকুইড মেটালটা স্ট্রিম লাইনে ফলো হতে বাধ্য হচ্ছে। So that is the main principle of the natural pressurized system. So despite the melt having a velocity well above the critical velocity, it tends not to suffer damage because there is effectively no room for the advancing meniscus to fold over or on itself to entrain the defect. So এটা আমরা যে বললাম ব্যাক প্রেসার করে লিকুইড মেটাল ব্যাক করে এবং এটা আবার ফোল্ড করে, এই ফোল্ড করলে পরে অক্সাইড গুলোকে ফোল্ড হয়ে যাচ্ছে এন্ড ডিফেক্ট জেনারেট করছে, সেই ধরনের কোনো সুযোগ এখানে থাকছে না, বিকজ লিকুইড মেটাল মুভ করার কোনো চান্সই পাচ্ছে না, যার ফলে সে সোজা সামনে যেতে বাধ্য হচ্ছে। So what is the problem of a natural pressure system? Apparently system is very good, যেহেতু এখানে কোনো মুভমেন্ট হচ্ছে না, নো স্প্ল্যাশিং হচ্ছে না, কোনো টার্বুলেন্স হচ্ছে না, সো ডিফেক্ট উইল বি মিনিমাইজড। তাহলে সমস্যাটা কি? সমস্যাটা হচ্ছে ইনিশিয়াল ভেলোসিটি। যেহেতু যে ফল যেটা করছে, আমরা জানি যে ক্রিটিক্যাল হাইট ভেলোসিটি হাইট মানে ভেলোসিটি অ্যাটেন্ড করে যে হাইটে, সেটা about 12 মিলিমিটার, বাট আমাদের মোল্ড হাইট অনেক বড় থাকে। সো এই লং হাইটে স্ক্রু হাইটে যদি লিকুইড ফল করে, at the base of the screw velocity can be 1.5 even more. even 4 meter per second. So এই হাই ভেলোসিটিটা লিকুইডটা কন্টেইন হচ্ছে, টার্বুলেন্স হচ্ছে না, স্প্ল্যাশিং হচ্ছে না ইন দ্য রানার অর ইন দ্য গেট, বাট এই 4 মিটার পার সেকেন্ডে এই লিকুইডটা মোল্ডের ভিতরে ঢুকছে। এই হাই ভেলোসিটিতে যখন সে মোল্ডে ঢুকলো, সে মোল্ডের ওয়ালের মধ্যে যে বাড়ি হাই ভেলোসিটিতে ইম্প্যাক্ট করবে, মোল্ড ওয়াল ভেঙে ফেলবে, স্যান্ডগুলোকে লুজ করে দিবে, ইরোশন হবে, অ্যান্ড ভেতরে মোল্ডের ভিতরে ক্যান জেনারেট টার্বুলেন্স বিকজ অফ দ্য হাই ভেলোসিটি। সো রানিং সিস্টেমের মধ্যে সে কন্টেইন হলো, কিন্তু মোল্ড ক্যাভিটিতে যে নিয়ে সে সিমিলার প্রবলেম জেনারেট করবে। সো অলদো রানিং সিস্টেম সে তার পারপাস সার্ভ করেছে, গেটিং ইয়েকে লিকুইডকে টার্বুলেন্স হতে দেয় নাই, কিন্তু বিকজ অফ দ্য ইনিশিয়াল হাই ভেলোসিটি liquid metal enters into the mold cavity at very high velocity. So again, the casting will be damaged. So that is the problem of naturally pressurized systems. So the naturally pressurized system approach require complete separate mechanism to reduce the velocity of the melt to the index. তাহলে পরে আমাকে যেটা করতে হবে, এই ভেলোসিটিটা রিডিউস করার জন্য কোনো একটা ব্যবস্থা করতে হবে। এখন আনপ্রেসারাইজ সিস্টেমে যে মেথড আমরা ইউজ করব, প্রেসারাইজ সিস্টেমে যে মেথড আমরা ইউজ করি, এইটার মধ্যে টোটালি ডিফারেন্ট। এটার মধ্যে যে সমস্ত মেথড ইউজ করা হয় সেটা গেটিং সিস্টেমের সাথে আদৌ কোনো সম্পর্ক নেই, বিকজ we tend to use filter, we tend to use runner extension, surge control, vertical fan gate, use of vortices. So these are the totally separate mechanism যেগুলো আমরা এই রানিং সিস্টেমের মধ্যে একটা সাম সর্ট অফ ব্যারিয়ার হিসেবে দেই, যাতে করে লিকুইড মেটাল ওই ব্যারিয়ারের কারণে ভেলোসিটি ডিক্রিজ করতে বাধ্য হয়। সো ফর এক্সাম্পল ফিল্টার, আমরা যদি রানারের মধ্যে, রানারের যে চ্যানেল যেটা আছে সেই চ্যানেলের মাঝখানে যদি এরকম একটা ফিল্টার দেই, ফিল্টার মানে হলো যে একটা সিরামিকের একটা ব্লক, যে সিরামিকের ব্লকের ভিতরে অনেক চিকন চিকন ছিদ্র আছে। সো লিকুইড মেটাল এর ভিতর দিয়ে যখন যাবে, এই চিকন ছিদ্রের ভিতর দিয়ে যখন যাবে, ভেলোসিটি ডিক্রিজ করতে বাধ্য হবে। যদিও ফিল্টারের কাজ ডিফারেন্ট, আমরা পরে দেখবো। ফিল্টারের মেইন কাজ হলো রিমুভ ইম্পিউরিটিস, বাট রিমুভ ইম্পিউরিটিস ছাড়াও সে ইট ক্যান রিডিউস দ্য ভেলোসিটি। সো দেয়ার আর আদার মেথড উই আর মেনশন হিয়ার, উইল ডিসকাস অ্যাবাউট দিস লেটার অন। সো এখানে আমরা যেটা বলতে চাচ্ছি সেটা হলো the pressurized system is good maintaining or minimizing turbulence in the gating system, but initial velocity do the much damage, and এই ইনিশিয়াল ভেলোসিটিটা গেটিং সিস্টেম মধ্যে রিডিউস করার জন্য আমাদের এক্সট্রা কিছু প্রিকশন নিতে হবে, এবং তার মধ্যে এগুলো কয়েকটা উল্লেখ করা হবে। সো আমরা মোটামুটি 3 ধরনের সিস্টেম পেলাম, একটা হলো আনপ্রেসারাইজ সিস্টেম, একটা হলো প্রেসারাইজ সিস্টেম, এবং আরেকটা হলো স্লাইটলি প্রেসারাইজড অর ন্যাচারালি প্রেসারাইজ সিস্টেম। এবং এগুলো নর্মালি আমরা বাই অবজার্ভিং দ্য গেটিং রেশিও আইডেন্টিফাই করি, ঠিক আছে? এবং গেটিং রেশিও যেটা বলে সেটা হলো যে 3টা মেইন এলিমেন্ট যেটা আছে, একটা হলো স্ক্রু, একটা রানার, একটা গেট, এবং এই 3টা এরিয়ার মধ্যে যে রেশিও সেটাকে বলে গেটিং রেশিও। রেফারেন্স পয়েন্ট অলওয়েজ স্ক্রু বেজ হিসেবে ধরা হয়। স্ক্রু বেজের যে এরিয়া সেটা হলো 1, এবং তারপরে কিভাবে যাচ্ছে। সো যেমন 1 to 4, এটা কি মিন করছে? সেটা হলো স্ক্রু বেজ এরিয়া 1 লেটস সে 1 সেন্টিমিটার স্কয়ার যদি হয়, তাহলে পরে রানারের এরিয়া হবে 2 সেন্টিমিটার স্কয়ার, এবং গেটের এরিয়া হবে 4 সেন্টিমিটার স্কয়ার। তার মানে এটা কোন ধরনের সিস্টেম হলো? সামনের দিকে যত যাচ্ছে এরিয়া তত বাড়ছে, তার মানে দিস ইজ অ্যান আনপ্রেসারাইজড সিস্টেম। আবার যদি বলি লেটস সে 1:0.75:0.5, তার মানে রেশিওটা কমতেছে, স্ক্রু বেজ এরিয়া থেকে রানার এরিয়া ছোট, রানার এরিয়া থেকে গেট এরিয়া ছোট, সো ইট ইজ এ প্রেসারাইজড সিস্টেম। ওকে, সো এই ধরনের নানান ধরনের গেটিং রেশিও কমনলি ইউজ করা হয়। এখানে কিছু এক্সাম্পল আমরা দিচ্ছি। সো গেটিং রেশিও মানে স্ক্রু বটম এরিয়া is to runner area is to gate area. Gate area mean করে টোটাল গেট এরিয়া, দুইটা গেট ইউজ করি, দুইটা গেটের যোগফল। তাহলে প্রেসারাইজ সিস্টেম কমনলি ইউজ করা হয় যেমন 1.8.6 অথবা 1.8। আনপ্রেসারাইজ সিস্টেমের মধ্যে 1 to 4, দিস ইজ দ্য কমন আনপ্রেসারাইজ সিস্টেম। আমরা ডিজাইন করার সময় হয়তো এই সিস্টেম, এই রেশিওটা ইউজ করব। ইট ক্যান বি 1 to 2 অ্যাজ ওয়েল। ন্যাচারাল সিস্টেম যেটা, সেটা হলো স্লাইটলি ইনক্রিজ করা হচ্ছে। 1.1 মানে 10% increase all the way. So এটার চেয়ে আবার 10% বাড়ানো হয়েছে এখানে। So 1, 1.1, 1.2. So this is the natural system. And naturally pressurized মানে এর চেয়ে একটু কম করা হচ্ছে, যেহেতু প্রেশারাইজড করা হচ্ছে so এর চেয়ে একটু কম। সামটাইমস আমরা এটা ইউজ করি, অথবা ইভেন এখানে 1 থাকার কথা ছিল, আমরা এখানে 1.1 থাকার কথা ছিল, এখানে 1 করা হয়েছে, এখানে 1.2 থাকার কথা ছিল, 1 করা হয়েছে। সো খুব একটা মডিফাই করা হয় নাই, জাস্ট প্রেশারাইজ করা হয়েছে। সো ন্যাচারাল সিস্টেম, ন্যাচারালি প্রেশারাইজ সিস্টেম কাছাকাছি। ওকে, সো 3 ধরনের সিস্টেম গেল। তাহলে পরে আমরা আবার সামারি করি। while designing the system আমরা টপ পুরিং এবং বটম পুরিং যদি কম্পেয়ার করি, উই উইল অলওয়েজ ইউজ বটম পুরিং সিস্টেম। তার মানে আমরা চেষ্টা করব লিকুইড মেটালটা যেন নিচ থেকে মোল ক্যাভিটিতে উঠে। সো মোল ক্যাভিটির নিচে থাকবে গেট, যে গেটটা অ্যাটাচ থাকবে রানারের উপরে। সো রানারের উপরে থাকবে গেট, সো রানারের উপরে থাকবে গেট এবং তার উপরে থাকবে কাস্টিং। সো লিকুইড মেটাল হরাইজন্টাল রানার দিয়ে অলওয়েজ উপর দিকে উঠবে। সো দিস ইজ দ্য bottom pouring system. We'll prefer bottom pouring system in our design. At the same time, we'll prefer unpressurized system. তার মানে আমরা লিকুইড মেটালকে যখন ফ্লো করবে, সামনের দিকে এরিয়া will be gradually increased. Probably we can use slightly pressurized system or naturally pressurized system, but we'll never use pressurized system, যেখানে লিকুইড মেটালের ভেলোসিটি is continuously increased. Okay, method used often conflict with each other. For example, attempts to fill the mole cavity rapidly can result in high velocity, and which can generate mole dilution and turbulence. So we have to decide first, based on the casting itself and the quality of the casting required, which kind of system we will use. If the supplier or if the buyer can tolerate a certain degree of defects, আমরা সেই হিসাবে ডিজাইন করব। As a result, any engaging system will generally be a compromise among the conflicting design requirements. Relative importance of consideration being determined by the specific castings and its molding and pouring conditions. So, based on the requirement, we will use a particular system. So, in general, contributing factor in the design should be these 6 points. Firstly, we have to decide whether top pouring or bottom pouring, or whether it is pressurized and whether it is pressurized or not pressurized system. Then the pouring temperature. This is critical because the temperature of the liquid metal controls the fluidity of the metal and it controls the solidification aspects of the metal. We have seen earlier. Type of the pouring equipment, or at what point we are pouring the liquid metal and which equipment we are using, whether it is a ladle or we are pouring directly from the ladle to the mold cavity, or we are using a pouring cup, conical pouring cup, or we are using a pouring basin. All these two are different. We will see later. The rate of pouring is also a critical factor because it will govern the velocity. Size and type of the runner. In fact, this will control the whole gating system. We will design the gating system based on a particular pouring rate. Size and type of the runner and screw, size, number, and location of inlet. Okay, so while designing, we'll firstly consider this thing, then we'll design this one and these two based on this four. Okay, let's have a 5 minutes break. Any question on this so far we talked about?
Sir, I had a question.
Yes.
So in the X-ray image of when the bad design of the bottom pouring system led to the fountaining effect, you
Yes.
showed that there were cracks that showed up.
Yeah.
So are those cracks solely created because of the oxide films, or are there any other reasons?
Okay, we are talking about this one.
Yes, sir.
Later we'll see that most of the defects generated because of this oxide film. And the defects usually are cracks, gas porosity, shrinkage cavity. So these are the common defects in a casting. And all defects can be initiated on top of an oxide film. So that's why turbulence is the critical issue here. If the turbulence is occurred, oxide can generate and enter into the liquid metal. And when we fold an oxide film, and if we introduce me myself, we have to learn more about painting, how to paint it, paint video. কিভাবে করে বলো, আমাকে সেন্টারে কিভাবে আনতে পারি? হচ্ছে না তো, হচ্ছে না। ওকে, যতটুকু পেরেছি, যেটা বলেছি যে অক্সাইড মনে করে একটা A4 সাইজ পেপার, ঠিক আছে? সো A4 সাইজ পেপার যদি হয়, অক্সাইড ফিল্ম, এটা নিচে আছে লিকুইড মেটাল। সো এই সারফেসটা লিকুইড মেটালের সাথে বন্ডিং আছে, ওয়েটেড বাই দ্য লিকুইড মেটাল। সো এখানে কোনো বাতাস বা কোনো এয়ার বা কোনো ধরনের গ্যাস নাই, ঠিক আছে? ইট ইজ বন্ডেড উইথ দ্য লিকুইড মেটাল। অন দ্য আদার হ্যান্ড, এই অক্সাইড ফিল্মের উপরে যেটা আছে সেটা হলো এয়ার। সো এটা হলো ওয়েট সারফেস, এটা হলো ড্রাই সারফেস। এই ড্রাই সারফেস হওয়ার কারণে যখন এটা ফোল্ড হয়ে যায়, এরকম যদি ফোল্ড হয়ে যায়, তোমরা কি দেখতে পাচ্ছ?
Yes sir,
যদি এরকম যদি ফোল্ড হয়ে যায়, তার মানে কি হচ্ছে, উপরে এই পাশটা অক্সাইড, এই পুরাটা অক্সাইড ফোল্ড যদি হয়ে যায়, অক্সাইড ইজ নট ওয়েল্ডেবল। কারণ এর উপরে চারিদিকে লিকুইড মেটাল আছে, দে বন্ডেড ভেরি ইজিলি। এই পাশে বন্ডেড হচ্ছে, এই পাশে বন্ড আছে, সবকিছু ঠিক আছে, কিন্তু এই মাঝখানে যে জায়গাটা, যে জায়গার মধ্যে অক্সাইড লেয়ার দুইটা একসাথে মিশলো, এই মিশলো কথাটা ঠিক না, কারণ এখানে কখনোই বন্ড ফর্ম করবে না, বিকজ দে আর ড্রাই। এর উপরের লিকুইডের সাথে বন্ড আছে, এর নিচের সারফেস এই লিকুইডের সাথে বন্ড আছে, চারিদিকে বন্ড আছে, কিন্তু ভিতরে কোনো বন্ড নেই এই ভিতরে জায়গাটা। as a result, this will act as a crack inside the liquid metal. So oxide যখন ফোল্ড হয়ে যায়, এই ফোল্ড জিনিসটাই একটা ক্র্যাক হিসেবে কাজ করে। জাস্ট ইমাজিন গ্রে কাস্ট আয়রন। তোমার গ্রে কাস্ট আয়রন ম্যাক্রো স্ট্রাকচার দেখেছো?
yes দেখেছি।
গ্রাফাইট ফিল্ম, যেটা গ্রে কাস্ট আয়রনের মধ্যে গ্রাফাইট ফিল্ম থাকে, তাই না?
ফ্লেক্স,
গ্রাফাইট ফ্লেক্স, সরি গ্রাফাইট ফ্লেক্স থাকে। এই গ্রাফাইট ফ্লেক্স মানে এখানে ভিতরে পাউডার, এই পাউডার থাকার কারণে এর মধ্যে কোনো বন্ড নাই, যার কারণে সেটা ডিফেক্ট হিসেবে কাজ করে। এই এক্স্যাক্টলি সেম, যে এটাও একটা ডিফেক্ট হিসেবে কাজ করে, কারণ এখানে কোনো বন্ড নাই। সো ইট অ্যাক্ট অ্যাজ এ ক্র্যাক। সো দিস ইজ এ ক্র্যাক। অন দ্য আদার হ্যান্ড, এর চারিদিকে এর উপরে আছে অক্সাইড, এবং এই অক্সাইড থাকার কারণে আমরা সলিড ডিভিশন পড়ার সময় বলেছিলাম, অক্সাইড is responsible for nucleating gas porosity. So এইখানে সে গ্যাস পরোসিটিও নিউক্লিয়েট করে। আরেকটা ডিফেক্ট আছে, শ্রিঙ্কেজ ক্যাভিটি। শ্রিঙ্কেজ ক্যাভিটি যখন ফর্ম করে, লিকুইড মেটাল পুরাটা লিকুইড মেটালে ভরা আছে, যখন এর ভিতরে ক্যাভিটি জেনারেট করে, ক্যাভিটি কেন জেনারেট করে? বিকজ এখানে একটা টেনশন কাজ করছে, লিকুইড মেটাল শ্রিঙ্ক করছে বিকজ অফ দ্য সলিডিফিকেশন শ্রিঙ্কেজ, কিন্তু সে মোল্ডের ভিতরে রেস্ট্রিক্টেড আছে। তো মোল্ডের সারফেসের সাথে সে লেগে আছে, কিন্তু ভিতরে মানে এটা আসছে শ্রিঙ্ক করতেছে সলিউশন শ্রিঙ্কেজ হওয়ার কারণে, যার কারণে ভিতরে একটা নেগেটিভ প্রেসার। সে তার মানে উপরে সারফেসে টেনে ধরে আছে, কিন্তু সে শ্রিঙ্ক করতে চাচ্ছে। সো একটা টেনসাইল ফোর্স কাজ করে, এবং এই টেনসাইল ফোর্সের কারণে ক্র্যাক জেনারেট করে। যদি এর ভিতরে কোনো অক্সাইড ফিল্ম থাকে, এই অক্সাইড ফিল্ম থাকার কারণে ভেরি ইজিলি ক্র্যাক ক্যান জেনারেট। যার ফলে আমরা যখনই কোনো শ্রিঙ্কেজ ক্যাভিটিকে ক্লোজলি অবজার্ভ করি, আমরা দেখি যে ইট অলওয়েজ অরিজিনেটস ফ্রম এ ক্র্যাক অর এ অক্সাইড ফিল্ম। সো অক্সাইড ফিল্ম নিজ এ ব্যাড, বিকজ এটা ক্র্যাক হিসেবে কাজ করে। এছাড়াও এই অক্সাইড ফিল্মের উপরে গ্যাস পরোসিটি নিউক্লিয়েট করতে পারে, এই অক্সাইড ফিল্মের উপরে shrinkage cavity increase করতে পারে। So these are the three common defects in casting or three main defects in the casting. Other defects এর ভিতরে sand particle আছে, inclusions আছে, there's some different minor things. These are the three main defects. তারপরে আমরা আরেকটা ডিফেক্ট কথা বলবো, হট টিয়ার, লিকুইড অবস্থায় টিয়ার করা। এই সব কিছু ক্যান জেনারেট অন টপ অফ অক্সাইড ফিল্ম। That's why we are saying that turbulence is so important. So এখানে যেহেতু টার্বুলেন্স হয়েছে, এখানে যদিও এখানে লেখা নাই লিকুইড অ্যালয়টা কি, কিন্তু আমরা জানি যেহেতু প্রফেসর ক্যাম্বেল অ্যালুমিনিয়াম নিয়ে কাজ করে বেশি, সো বেসিক্যালি ইট শুড বি অ্যান অ্যালুমিনিয়াম কাস্টিং, এবং অ্যালুমিনিয়াম কাস্টিং এর মধ্যে অক্সিডেশন হওয়া ভেরি ইজি, যার কারণে আমরা এক্সপেক্ট করতেছি যে এখানে এই বিকজ অফ দ্য টার্বুলেন্স অক্সাইড ফিল্মের ভিতরে মিক্স আপ হয়ে গেছে, এবং এই অক্সাইড ফিল্মের মধ্যেই ক্র্যাক এন্ড এখানে গ্যাস বাবল ক্রিয়েট করেছে। সেখানে যেটা বলেছে যে কোথায়, the final casting showing subsurface bubble and internal crack, যেহেতু চারিদিকে সলিডিফাই হয়ে গেছে, সারফেস টারফেস পুরোটা সলিডিফাই হয়ে গেছে, সো ভিতরে গ্যাস যেগুলো আছে, বাবল যেটা আছে সেটা সারফেসে আর বেরিয়ে যেতে চান্স পায় নাই, তো ভিতরে বাবল হিসেবে থেকে গেছে এবং কিছু ক্র্যাক আছে। ঠিক আছে?
Yes, sir.
Okay. So let's have a 2 minute, another 2 minute break. এই 2 মিনিটের মধ্যে আমি চেষ্টা করি এটা কি করে করতে হয়। Okay, I stop the sharing. Oh, okay, তাহলে এটা কি হলো? This is gallery view. Oh, okay. দুইটা একসাথে। Okay. ওকে, আমরা শুরু করি। প্রেসার সিস্টেম আমরা শেষ করলাম। ওকে, কন্ট্রোল শেষ আছে। So our next topic is surface tensile control failing in gating system. We know about surface tension, and if the section thickness of the channel is very small, then surface tension force come into effect. And because of this surface tension, PQ metal may not enter the mold cavity at all. So if the section is too narrow, or if there is a curved or reduction in filling pressure resulted, the surface tension resistance cannot enter the cannot limit the liquid metal to enter into the mold cavity. So even the worst case scenario, the mold can be emptied out because of this surface tension. So surface tension is a big issue in small section casting or casting having a small section. For example, here, this is the ideal case scenario. So it is a hemispherical shape channel up to different radius, common principal radius. So this is the internal pressure, Pi, because of which liquid metal flows into the mold, into the channel, and this is the external pressure, Pe, and because of that, liquid metal cannot enter the mold cavity or cannot enter the flow into the channel. So for this type of design, the filling would be allowed only when this equation is prevailing. That means internal pressure minus external pressure equal to surface tension multiplied by 1 by radius of these two. If the mold is circular, that means R1 is equal to R2, and in that case, the formula is reduced to twice gamma by R, twice surface tension divided by radius. So this is the general formula of narrow section channel through which liquid metal is trying to enter into the channel. So if the mold is weighted by the liquid, that means weighting means there is no resistance. In that case, this term becomes negative. If this term becomes negative, then if we move this from right side to left side, it becomes positive. So Pi plus this 2. So that means it is helping liquid to enter into the mold. So if the liquid metal weighting the mold, this term becomes negative and liquid metal can easily enter into the mold cavity. This is not the general case. Generally, the mold is usually non-weighting, and for that, this formula is prevailed, and this is for circular mold. So internal pressure minus external pressure should be greater than this resistance term. If it is greater and if it is positive, then only liquid metal can enter into the filling system. So what is Pi? The positive pressure will be experienced by these two factors. One is atmospheric pressure, that means directly observing from the sprue. So the atmospheric pressure is forcing the liquid through the sprue to enter into the mold cavity. And there is another one which is called metal head pressure, H0G. So because of the height of the mold, height of the sprue, it will experience the metal head pressure. So metal head pressure and atmospheric pressure, these are the two positive components or internal pressure that aids flow of liquid metal. Resistance will be offered by two aspects. Again, here is Pa, which will be observed or experienced through the mold because mold is open to the atmosphere. So this Pa will be introduced into the mold cavity through the mold, and at the same time there is a Pm, and Pm means mold gas pressure. Firstly, there is air into the mold cavity, empty mold cavity. So as liquid metal enters into the mold cavity, the air inside the chamber or inside the mold cavity, they will offer resistance not to flow the liquid metal. And at the same time, at the mold itself, there are some gases. For example, moisture. For example, other gases, atmospheric gases as well. So they also offer resistance not to enter the liquid metal into the mold cavity. So these are the two external pressure that prevents liquid metal allow into the channel. So positive pressure is the negative pressure. So there is a PA, there is PA, we remove this PA, so ultimately becomes H rho G minus PM, and this should be greater than surface tension resistance offered by the surface tension. So this is our general formula for narrow section mold cavity for filling the mold cavity against the surface tension. Now let us consider these three aspects. Sometimes when mold is prepared, uh, the mold are usually vent the mold using a small thin steel the steel wire. They tend to vent the mold cavity. What is the purpose of bending? This venting, it is good or bad? Does it affect the filling of the mold? What happens during venting? During venting, or if you vent the mold, the gases inside the mold can easily goes out. As a result, this PM becomes 0. So the minus term becomes 0. So these terms become greater. As a result, liquid metal will have more opportunity to enter into the cavity. So bending helps filling of the mold. So it is a good for mold filling. What about atmosphere? Does atmospheric pressure any help? In the final equation, there is no term for atmospheric pressure. Atmospheric pressure cancel out from the positive and the negative. So role of atmosphere is nothing, is 0. There is no effect of atmospheric pressure in filling the mold cavity. Does vacuum casting help? What is the meaning of vacuum casting? Vacuum casting means atmospheric pressure is reduced. The pressure is reduced. So atmospheric pressure 101 kPa, and we can minimize it 10 to the power minus 3, 10 to the power minus 5 kPa, etc. So basically, it is a PA in the reduced term, reduced value. Since PA is cancelled out in the final equation, so atmospheric pressure and vacuum pressure doesn't have any effect. So you can, vacuum casting will be no good in mold filling. Atmospheric pressure will be no good in mold filling, but bending will help. Sometimes there is a 5-point question, what about the use of vacuum casting help mold filling or not, or whether atmospheric pressure can help mold filling or not, etc. But what about vacuum assisted casting? What is the meaning of vacuum assisted casting? That means mold is kept open to the atmosphere, but we're applying pressure. No, sorry, this is wrong. Here, the mold is kept under vacuum, but the filling is open. That means during filling, we're openly pouring the liquid metal onto the pouring basin. So H rho G becomes effective, and at the same time, PA is also become effective because it is open to the atmosphere. But on the other hand, since mold is inside the vacuum, so we sucked out the PM as well as we sucked out the PA. So PA become negative, 0, not 0, 10 to the power minus something. So we can effectively call it 0. And at the same time, PM becomes 0. So these two terms is eliminated. But PA is remained, H rho is remained. So ultimately, the formula becomes PA plus H rho G is greater than twice gamma rho. So we're using PA to help the liquid metal to flow into the mold. So vacuum casting is different from vacuum assisted filling. In the vacuum casting, all the thing, that means filling and the mold is kept inside the vacuum. That's why vacuum doesn't have any help. But in the vacuum assisted filling, the mold is kept in the vacuum, but the filling is done normally. Okay, let's see how it helps. For example, let's do a turbine casting, turbine blade casting. So in a turbine, you see that this is a thicker section, and it becomes gradually thinner and thinner and thinner. So the trailing is the thinnest one. Now, if we use this formula, G is equal to 10 meter per second. So, okay, let's 10, call it 10. Density is 2500 for aluminum casting, let's say. Gamma for aluminum casting is 1 Newton per meter, and atmospheric pressure is 10 kPa, 100 kPa, and 101 to be exact. Okay, forget about that one. Roughly, this is 100 kPa for easy calculation. So the resistance term twice gamma by r is 2 kPa if this section is about 1 millimeter thick. That means radius is equal to 0.5 millimeter. So 0.5 millimeter radius twice gamma by r becomes 2 kPa. And if the trailing edge, that means which is 0.1 millimeter radius, the pressure right hand side becomes 10 kPa. Now, for normal casting, if the formula is this one, and if we tend to ignore this PM, so the solely positive pressure is H rho G. So if we calculate H rho G for 100 millimeter height casting, then the value becomes 2.5 kPa. That means the positive pressure is 2.5 kPa, and this 2.5 kPa is forcing the liquid metal to enter into the mold cavity. But to enter into the mold cavity, for 1 millimeter section, we need only resistance is 2 kPa. So the liquid metal is moving at 2.5 kPa, resistance is 2 kPa. So liquid metal can easily enter into the section having 1 millimeter section. On the other hand, to enter into the trailing edge, which is only about 0.1 millimeter radius, the resistance is 10 kPa, but we are allowing or forcing the liquid metal using 2.5 kPa. So liquid metal cannot enter into these sharp points. So as a result, it will have a defect in this area. So it will just bend it here, and we will have incomplete castings. So trailing edge has no chance of failing. But if we use vacuum assisted filling, that means if we use this formula, then H rho G is 2.5 and PA is equal to 100. So total become 103.5. Actually, this is we are using 101. Anyway, this is 102 or 103.5, whatever it may be. So resistance is 10 kPa, but we are forcing the liquid using more than 100 kPa. So liquid metal can easily enter into the trailing edge. So for casting, having this narrow section, vacuum assisted filling is of great help. So to summarize, for thin casting, section having smaller than 1 to 2 millimeter, surface tension is an important parameter. It has a strong influence in filling the mold cavity. Filling will be only possible if we use external force. External force can be vacuum, can be atmospheric pressure, or can be centrifugal force. Later we see that there is a casting process commonly called centrifugal casting, where velocity is used to centrifuge the liquid metal into the mold cavity. So because of this high velocity and because of the high centrifugal force, liquid metal can enter into the mold cavity. So this type of external force is needed to enter into the mold having this small section. So metal head required to force the liquid metal into small section, ignoring atmospheric pressure. So this H2 is equal to twice gamma by R. So H is equal to twice gamma by rho G R. So if the section is half, if you reduce the section by 2, head will be doubled. You need double head. So screw height will be doubled. On the other hand, if the section becomes circular, again the head will be doubled. So we have to keep in mind these two aspects during designing the mold, designing the running system.
Sir,
yes.
Sir, how the section being circular head will be doubled again?
Okay, in that case, you have to use the general common formula, this one. So if it is not circular, then we have two radius. If it's circular, then we have a twice radius because it is two equal. For that,
Sir, does that mean that for the thin section we are assuming the another radius that is not being taken into account to be pushed to infinity?
yes,
then what
one terms become infinity. So
then what does that physically mean?
This means 0. If it is a plate, if it's a plate,
Okay, and so the thing is, so if we want to fill a cylindrical section, we will need some pressure. But if we make it spherical, then it will take the double pressure. Is it meant so?
Yes, yes.
Okay, sir, I have understood.
No, just think as a plate and think as a circular thing. For plate casting, in this direction, R is infinity. It is so. In this direction, R is infinity. As a result, 1 by R is equal to 0. So
Okay.
we have only gamma by R. On the other hand, for circular section, this is R, this is R. So we need 2R. That's why twice gamma by R. So for plate casting, we have gamma by R. For circular casting, we have twice gamma by R. So it is double. Okay?
Probably, sir, I am probably missing, sir, something. As far as I know, for a cylinder, if we consider two principal radii of curvature, one
Yes.
can be said infinity. That is flat, and other is zero. For plate, however, for a plate, there are two mutually perpendicular direction. Both are flat. So
No, no,
so
no, 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 no. Not both are flat.
okay.
Just consider this one.
Uh,
If it is circular, we have R1 and R2, and those two are equal, so we have a general R. So
oh, okay, sir. I think I have got it. We are considering the geometrical band plus the band of the liquid flow itself.
yes.
Okay, now I understood.
Okay, okay. So in short, if the section is thinner, surface tension will be experienced, and it will tend to prevent the liquid metal entering the mold. And because of that, we need external pressure to force the liquid metal into the mold cavity. Usually, two-way this is done. One is called high pressure die casting. That means we are forcing the liquid metal into the mold. And for example, if you want to reproduce a radius of 0.001 millimeter, that means thickness of the section is 0.001 millimeter, very small, very thin. And for that reason, pressure is required about 1 megapascal, that means 10 atmosphere. So we can calculate it using the previous formula. But generally, for high pressure die casting, 100 megapascal is used. 100. One is required, but practically 100 is used. And if we enter this 100 megapascal into our formula, the R, the radius of the section becomes 10 to the power minus 8, which is the size of a radius, diameter of an atom. So can you understand what I'm saying? That if we use 100 megapascal pressure, we can force the liquid metal to a section having a radius of 10 to the power minus 8 meter. And this is the dimension of an atom. So do we have any kind of casting that having this small size cross section? No, never. So why do we use this 100 megapascal high pressure in high pressure die casting? Second question, for centrifugal casting, if the casting velocity, that means this centrifugal force, 10 meter per second, it will produce a 10 G. 10 G, that means 100 meter per second square. Acceleration and better finer details of factor 11 can be added. And this is more than enough to produce a finer details of a casting. But in industry, we use 50 to 100 G, very high, where 10 G is enough to produce a surface finish of factor 11, we use 50 to 100 G. So where we are using this high pressure, industrial production process use such a high value of pressure or centrifugal force. So commonly this is a question usually appeared in your exam. Uh, can you understand what I'm saying? That means only small fraction of the pressure required is more than sufficient to produce a casting, good quality casting. But we are using a tremendous force to enter into the mold to force the liquid metal to enter into the mold cavity. Actually, this is nothing to do with mold filling. We are studying the gating system, and the gating system is used to fill the liquid metal into the mold cavity. So we are practically studying filling system, but this high pressure has nothing to do with the filling of the mold cavity. This high pressure only used so that defects cannot generated inside the mold. Later, while we is studying the feeding system, then we will discuss this whole thing. Because of this high pressure, a defect cannot be generated inside the mold, inside the casting. And for that matter, we use this high pressure. Okay, so this is nothing to do with filling the mold cavity. Okay, so another last topic is surface finish, another important issue. So if the metal head pressure is very high, what will happen? From our earlier equation, we see that if the external pressure is very high, then liquid metal can be forced to enter into the mold cavity. So if the total pressure is very high, liquid metal will enter into the mold cavity. Not only entered into the mold cavity, it can enter into the space between two sands. Between the sands, spacing of the sands, it can enter into. As a result, the surface finish will be very bad. So for sufficiently high metal head pressure, surface tension no longer able to resist metal penetration, and casting with rough surface will be resulted. So this is at all not wanted. We tend to do something so that this kind of thing never happens. And to resist metal penetration, what we can do, according to formula, we can reduce the R value. That means we can increase the right hand side term, gamma by R. As gamma is constant for a particular liquid metal, so we can reduce the R so that the right hand side term become much higher. And how can we reduce the term? We can reduce finer sand so that the space between the sand becomes finer. So liquid metal cannot enter those spaces. Alternatively, okay, it is an obvious problem, because if we reduce the size of the sand, permeability will be decreased. You know, permeability, you have test to measure the permeability of green sand. If we reduce the fineness of the sand, permeability will be reduced. So mold gas and the gas inside the liquid metal cannot escape from the mold. As a result, gas defect will generate. So reducing the size of the sand is obviously has problem. One thing we can do, we can still use the finer coarse sand at the other side, but at the mold surface, inside surface, we can use finer sand in the form of mold wash. So it can be a liquid wash. That means finer sand in suspension with a liquid material. So you can use, we can coat the inside mold cavity using this mold wash, so that ultimately when you dry the mold cavity, at the inner surface of the mold cavity, we have a fine coat comprising finer sand, and it will prevent the liquid metal entering the mold cavity. So either use finer sand. If it is not possible, then use mold wash, so that liquid cannot penetrate into the mold cavity and surface will be higher. So this is about introduction to the casting. If we remove the sharing. So today's lecture includes the final part of designing gating system, introduction of gating system. Here we are saying that two aspects of gating system we should consider while designing. One is top pouring system or bottom pouring system. Obviously, top pouring system would introduce lots of turbulence inside the mold cavity. inside the mold. As a result, casting can be damaged. On the other hand, the bottom pouring system has the capacity to reduce the metal velocity as liquid metal will enter from the bottom and goes up against the gravity. So it will have a greater opportunity to reduce the liquid pressure, reduce turbulence. As a result, casting quality can be enhanced. So as a result, we will use bottom pouring system during our design. And then there is another system which is called pressurized system or unpressurized system. And in the pressurized system, the area of the running system is continuously decreasing. That means from the screw to runner to gate, area is decreasing. As a result, velocity of the liquid is continuously increasing, and at the same time, the liquid is experiencing a certain back pressure, so that it come back and fill the liquid, the running system. So, filling the running system because of the back pressure, this is good, but the velocity of the liquid is increasing. It has two effects. One is it will fill the mold very easily with short period of time, so fluidity will have no effect. There is another good point, but the velocity increase in velocity will have turbulence and which can damage the casting. That is the very bad sign. On the other hand, there is an unpressurized system. In the unpressurized system, the running system is expanding as we progress, and because of this expansion, velocity is decreasing continuously. So it helps minimizing turbulence, mold erosion. But on the other hand, as it expanding, it will have a very high opportunity to not filling the running system completely. As a result, there will be great danger of air entrapment into the liquid metal and to cause gas problem and other problems. So we have to very precautious about how to design these aspects. But we use the bottom pouring system, the anti-pressure system, because it has a great advantage in producing good quality castings, but we have to be careful. There is another topic as well, which is known as slightly pressurized system. In this system, the channel follows the liquid metal. So it is always in contact with the liquid metal, and the area is slightly reduced as we progress. As a result, it always in contact with liquid metal, to it choke the liquid metal continuously. So liquid metal will have no opportunity to move around. So there will be no turbulence, no gas entrapment, and liquid metal will follow calmly. Not calmly, it is forced to follow in streamlined manner. But as during the fall of the liquid metal through screw height, the high velocity of the liquid metal is following, even increasing to certain limit. There is no opportunity of reducing this liquid metal velocity as we progress through the running system. As a result, liquid metal enters into the mold cavity at a very high velocity, and finally, although the running system serves its purpose to minimizing turbulence, but the high velocity of the liquid metal can damage ultimately inside the mold cavity. So we have to use certain measure to reduce this initial velocity at some point inside the running system. So common measures is to use filter, and there are some other measures as well we have mentioned in our lecture. We will discuss detail those things later on. Finally, we use another important aspect. When the casting thickness is very narrow, then liquid metal experience problem entering the mold cavity or entering the running system because of the resistance of surface tension. And the resistance of surface tension can be different depend on the casting geometry or running channel geometry. If the section is very narrow, then we have to force the liquid metal through the channel by using some external means. One can be high pressure, for example, high pressure die casting, or we can use centrifugal force as in centrifugal castings. We have seen that in real practice, we use very high pressure in high pressure die casting, very high pressure than necessary, and very high centrifugal force that is necessary. And these two are commonly used only to eliminate casting defects inside the casting. It has no purpose in filling the running system. Okay, any question? No question.
Sir, I had a question not about today's lecture, but about the course material.
Okay.
সেটা হচ্ছে স্যার যে লাস্ট কোর্সে তো মানে আপনি প্রোভাইড করেছিলেন লেকচার ম্যাটেরিয়ালস, বাট এবার I tried reading it from the books, especially like Campbell's boite. There's a lot more additional details as opposed to what was like explored in the lecture.
Yes.
So we khetre sir mane what should our approach be in terms of mane if we don't get the lecture material tahale?
আমি লেকচার তোমাদের তো সরি তোমাদের সলিউশন লেকচার ম্যাটেরিয়াল দেইনি না, আমি চেষ্টা করব দেওয়ার জন্য, ঠিক আছে? কনসাইজ ফর্মে আমার কিছু লেখা আছে। আমি বলেছি যে যেহেতু আমি আগামী সেমিস্টার থেকে মানে ওই স্লাইটলি প্রেশারাইজ সিস্টেমকে অ্যাডভোকেট করব, সেজন্য আমি নোটস যেগুলো তৈরি করেছি সেটা স্লাইটলি প্রেশারাইজ সিস্টেমের। সো আমার পুরানা নোটস যেটা আছে, যেখানে আমি গেটিং সিস্টেম আনপ্রেশারাইজ সিস্টেম ফলো করেছি, সেগুলো নোটস আছে ইন কনসাইজ ফর্ম, আমি তোমাদের সেগুলো দিয়ে দেবো, ঠিক আছে? তো আমাকে কিছুটা সময় দাও, আমাকে সপ্তাহখানিক সময় দাও, যাতে করে আমি একটু অর্গানাইজ করতে পারি। ইন দ্য মিন টাইম আমি এই উইকেন্ডে তোমাদের সলিউশনটা দিয়ে দেবো, ঠিক আছে?
ওকে
ওকে। সো যদি কোনো কোয়েশ্চেন না থাকে তাহলে আমরা আজকে এন্ড করি। সি ইউ নেক্সট টাইম।
স্যার অ্যাটেন্ডেন্স নেওয়া হবে না?
আমি তোমাদের এখানে পার্টিসিপেন্টের লিস্ট যেটা আছে সেখানে আমি দেখতে বুঝতে পারবো কারা কারা আসে নাই। ওকে, নতুন করে আর নিব না।